Hi everyone, this is Matt Teachout with Intro Stats, and today we're looking at a problem from my book. This is section 4A number 36. So this is again using a randomized simulation for a two-population mean hypothesis test. So let's read it. Number 36 says, go to stat key at lock5stat.com. Under the randomization hypothesis test menu, click on test for difference in means. Under the datasets menu at the top left, click on exercise hours. So this took a random sample of male adults, population 1, and a random sample of female adults, population 2. Use a randomized simulation and a 10% significance level to test the claim that the mean average amount of time that males and females exercises is the same. So what does this data indicate about the relationship between exercise hours and gender? Okay, so basically we're doing a two-population mean randomized simulation hypothesis test with a 10% significance level. And we're supposed to test the claim that they are the same. So again, we'll go ahead and do that. They said that male was population 1 and female was population 2. Remember, whenever you're dealing with a two population, it's really important to know what was population 1 and what was population 2. In this case, we're going to assume they're the same. So mu1, the population mean average exercise for males, is equal to mu2, the population mean average exercise hours for females. That's going to be the null hypothesis because they're equal. Meaning the alternative would have to be not equal. So we're going to do a not equal, so that would make this a two-tailed test. So let's go to stat key and go ahead and get our numbers. Alright, so here's stat key. And we're going for test for difference in means. Again, in the problems, you can kind of just follow the directions. It does tell you kind of what to click on. And we're looking for something about exercise. There it is, exercise male versus female. Looks like the fifth one down in the preloaded data sets. And there we go. So our mean average exercise hours for the sample of men was 12.4 hours per week, and the mean average for women in the data was 9.4 hours per week. We can see a couple things here. The sample size for men was only 20. It also looks a little bit skewed right. So that's going to fail the 30 or normal requirement. The women's data, however, did have 30, and it looks somewhat on the normal side. We do have quite a bit of women in the center of the graph. Well, actually, wait, there's this little outlier way out here. So maybe it's a little bit skewed right, but it's still going to pass the 30 or normal because we're at 30. But this is a good example of when we would use a randomized simulation. This data probably would not match up well with the traditional t-distribution test. Alright, so we're going to, again, we're going to assume the null hypothesis is true, and we're going to collect random samples under the premise the null hypothesis is true. So just click this 1,000 samples button a bunch of times. Remember, your samples, when you do this, will not be the same as mine. There will be some variability in our answers and when you do randomized simulation. Alright, so we're doing a two-tailed test, so we're going to go two-tail. Alright, now the problem did say use a 10% significance level. Okay, so we have to think about this. A 10% significance level for two-tail would mean you'd have to have 0.05 in each tail. So if you just put 0.05 in one of the tails, the other one will adjust. And there we got 90% in the middle, 5% in each tail. There's our 10% significance level broken up into two tails. Now this tells us where the tails start. So the difference, the sample difference, we want to know if the sample difference in this problem was 3. This was doing male minus female. So their male was group 1, female was group 2. So the computer thinks anything bigger, any difference bigger than 3.917 or lower than negative 3.667 would be significant. In our case here, our 3 is not significant. It actually is in here. It's not in the tail. Remember, so this would tell us that the sample data does not significantly disagree with the null hypothesis. So this the 3 hour difference between the sample means is not significantly different because it's not falling in the tail. All right, so now we need our p-value. Remember, this is not p-value, this is the significance level. So the p-value is the probability of this original sample data happening. So all we're going to do is, in this bottom box here, I'm going to put in the original sample difference of 3 hours. Now, if this was a right-tailed test, then this 0.103 would be the p-value. But this is a two-tailed test, so we have to consider both tails. So again, like say in the old days, we used to multiply the p-value by 2, the tail percentage by 2 to get the p-value, or you can simply add these two tails together. So 0.103 plus 0.103 is 0.206. That's going to be our estimated p-value. Again, your numbers when you use simulation might come out a little bit different than these numbers on this simulation I'm showing you, just because my random samples are not the same as your random samples, right? Sampling variability. So 0.206 is a very high p-value. So we're dealing with this could just be the work of sampling variability. In other words, the null might be correct, and maybe this 3 hour difference between the samples is just the result of sampling variability. That means we're going to fail to reject the null hypothesis, but the null hypothesis actually was the claim, right? We were claiming that they were equal. So it sounds like there is not significant evidence to reject the claim that the population mean average exercise hours for males and females are equal or are the same. Okay? And that'll do it for us. So I will see you next time.